Hello students, good time to all. And Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss metallic reflection at normal incidence condition. Let's begin. Metallic reflection. We have to consider a conducting medium, means that is a metal. Consider this is a metal. Or we call it as conductor. That is conducting medium, and that medium, let we choose that medium as non-conducting dielectric medium. This one as non-conducting dielectric medium, non-conducting dielectric medium. For our convenient, we can say this is medium 1, this is medium 1, and that medium 1 has permittivity epsilon 1, permeability mu 1, conductivity sigma 1, refractive index n1. Medium 1, which is non-conducting, or we can say it as dielectric medium. Similarly, this one as metal or conductor, we consider it as medium 2. Same thing here, permittivity epsilon 2, permeability mu 2, conductivity sigma 2, and refractive index n2. Let we consider a plane electromagnetic wave traveling from that of non-conducting dielectric medium incident on that conducting medium. So, we take an electromagnetic wave from this non-conducting dielectric medium incident on that of conducting medium at normal incidence. This is electromagnetic wave. If that monochromatic electromagnetic wave travelling from non-conducting dielectric medium to that of conducting dielectric medium means it is incident on that metal normally, then what happened? For normal incidence condition, we say that the angle of incidence, the angle of reflection and the angle of transmission all are 0 degree, and here the electromagnetic wave incident on that metal, then it is reflected back at that of normal incidence situation. It can be shown mathematically. The incident, reflected and refracted waves are represented. For incident, it is E I vector. Again look here, as we taken the electromagnetic wave, it has electric field and magnetic field vector, but the orientation of electric field either perpendicular to the plane of incidence or parallel to that of plane of incidence. In that particular situation, we consider that the E vector is parallel to the plane of incidence. Anybody can taking E vector as perpendicular to the plane of incidence, then the result will be same. So, here we taken E vector as parallel to that of plane of incidence and that electromagnetic wave incident on that of metal normally. Incident electric field vector, its amplitude E O I into e to the power I k I dot r minus omega t, k I is the propagation vector for that of incident wave. Equation number 1. Similarly, for that of magnetic field vector, the relation between S vector and E vector, as S vector is equal to k cross E vector divided by omega into mu, permeability of that of medium. So, here for that of incident wave, it is S I vector is equal to k I vector cross E I vector divided by omega into, for that of medium 1, the incident wave are that of medium 1 mu 1, equation number 2. Then for reflected wave, it is E r vector is equal to E O r, this is the amplitude for that of reflected wave, into e to the power I k r dot r vector minus omega t, k r is the propagation vector for that of reflected wave, equation number 3. At that of same time, magnetic field vector for that of reflected wave, we relate E r vector to that of H r vector, that is equation number 4. That reflected wave again in that of medium 1. Next, for transmitted wave, E t vector is equal to its amplitude E o t vector into e to the power I k t dot r vector minus omega t, k t, that the propagation wave of transmitted wave, k t. Next, relation between S t and k t, as that transmitted wave in that of medium 2, here we prefer mu 2, that is equation number 5 and equation number 6. Mathematically, we show incident, reflected and transmitted wave. Look here, in that of second medium, it is conducting one metal, that is a conductor, and we have already studied when electromagnetic wave is propagating through that of conducting medium, then that transmitted wave, direction of propagation of transmission wave kT is represented as a complex quantity, and K2, let Kt is nothing but K2. For that of medium 2, in our simplicity we write it as K2. It is a complex quantity, that is alpha plus I beta. We have already derived that expressions in the section named as electromagnetic wave in conducting medium. So, the value of alpha is equal to omega mu 2 epsilon 2 divided by 2 under root 1 plus that under root, next beta, this one. For a good conductor, that quantity sigma divided by omega epsilon 2 is very greater than 1. Therefore, in that of expression we can neglect 1, that is why we achieve alpha is equal to beta. This one is equal to omega mu 2 sigma divided by 2 under root. This is the condition for good conductor, alpha is equal to beta. Next, we can use the boundary condition for E vector and S vector are that of interface, that interface which is separating these two media. Applying the boundary condition at the interface, which separating the two media named as medium 1 and the medium 2. For electric field vector, so E vector for medium 1, the tangential component is same as E vector for medium 2, that the tangential component. Here an important point you have to notice, the component of electric field vector we choose parallel to that of plane of incidence. Here E vector is parallel to the plane of incidence, plane of incidence. What is the tangential component of medium 1? The tangential component of medium 1 as incident as well as reflected. For incident, we consider its magnitude term only. So, E O I and the cos of angle of incidence, as we treated E vector is parallel to that of plane of incident. So, its tangential component, so cos theta I minus, why we choose minus, as for reflected wave is just opposite to that of incident wave. Therefore, for reflected wave at that of medium 1, its tangential component, the amplitude factor OR cos theta r is equal to, in that of medium 2, that is E O T cos theta t. For normal incidence, theta I is equal to theta r equal to theta t 0 degree. So cos 0 as 1. So we have E O I minus E O R is equal to E O T. Equation number 7. This is for electric field. And next, for magnetic field vector, since we taken E vector is parallel to that of plane of incidence, and the relation between E vector and S vector, as E vector is perpendicular to that of S vector, then since it is tangential component, we prefer E O y cos theta, as E vector is parallel to that of plane of incidence. But in case of S vector, it is only for that of S vector, the tangential component medium 1 tangential component is same as medium 2 tangential component. Therefore, at the medium 1, that is for incident wave and reflected wave, the amplitude of incident wave H O I, amplitude of that of reflected wave O R. Next, at medium 2, it is the amplitude for that of transmitted wave. Or as we say, how E vector and S vector are related. How E vector and S vector are related. S vector is equal to k cross E vector divided by omega mu under that of medium, in which medium we consider it. So S O I, it is in medium 1. So it is written as K1 divided by, as we prefer only the magnitude part, mu1 omega E O y plus for S O R, that is K1 divided by mu1 omega E over K. This is medium 2, K2 divided by mu2 omega E O T, or common K1 divided by mu1 omega E O I plus E over is equal to K2 divided by mu2 omega E O T. Here is the condition for non-magnetic medium. For non-magnetic medium, mu1 is equal to mu2, that is equal to mu naught. Permeability of medium 1, permeability of medium 2 is nothing but permeability of that free space. And another relation, how K vector is related to the refractive index. Again that equation is established in the section when electromagnetic wave is propagating through that of conducting medium, as a relation K2 K1 divided by K2 is equal to N1 divided by N2. These relations are used. So the expression EOI plus EOR mu1 mu2 omega cancel out, as we say mu1 is equal to mu2 is equal to mu naught, that is K2 by K1 into EOT, or EOI plus EOR is equal to N2 by N1 into EOT. Let equation number 8. To showcase the reflectance and transmittance, or reflection coefficient or transmission coefficient, we have to require the EOI, EOR and EOT. Therefore, first we add equation number 8 to that of equation number 7. Adding equation number 7 and equation number 8. EOR cancel out, it has 2 times of EOI is equal to EOT plus N2 by N1 EOT. Or 2 EOI is equal to EOT as common 1 plus N2 by N1. Our requirement is EOT divided by EOI. That for which situation we taken it as parallel condition, when E vector is parallel to that of plane of incidence. Therefore, it will be 2 divided by 1 plus N2 by N1, which is equal to, taking that of LCM, in that of numerator side, it will be 2 N1 divided by N1 plus N2, that is equation number 9. Next, we have to show what is EOR to that of EOI. Then, as we say EOI plus EOR is equal to N2 by N1 EOT, N2 by N1 EOT in that of equation number 8. Our requirement is EOR to that of EOI. Therefore, in place of EOT we can replace it. In place of EOT we write EOI minus EOR. Therefore, EOI plus EOR is equal to N2 by N1, that is EOI minus EOR. The terms as EOI common 1 minus N2 by N1 is equal to minus EOR common 1 plus N2 by N1. Okay, we have to find EOR divided by EOI at that parallel situation. EOR divided by EOI, so it will be minus 1 minus N2 by N1 divided by 1 plus N2 by N1. Under simplification, we have EOR divided by EOI at parallel, that is N1 minus N2 divided by N1. Here N1 plus N2 divided by N1, N1 and N1 cancel out when that minus is multiplied. So we have N2 minus N1 divided by N2 plus N1, that is equation number 10. EOT divided by EOI at parallel situation and EOR divided by EOI at parallel situation. From that of expression we can easily showcase what is reflection coefficient or transmission coefficient. Now it can be further simplified from equation 9 and 10. From equation 9 and 10, from equation 9, EOT divided by EOI at the parallel is equal to, that is 2N1 divided by N1 plus N2. Let N1 is divided in that of numerator and denominator side. So we have obtained EOT divided by EOI parallel 2 divided by 1 plus N2 by N1, and from equation number 10, that is EOR divided by EOI at parallel situation, N2 minus N1 divided by N2 plus N1, dividing N1 on both numerator and denominator side. So EOR divided by EOI at parallel, that is N2 by N1 minus 1 divided by N2 by N1 plus 1. An important relation we can write here, but N2 is equal to C by omega K2. K2 is a complex one which is equal to C by omega in place of K2, that is alpha plus I beta. In starting of that video I mentioned it as K2 is equal to alpha plus I beta. So this one is a complex quantity, and N1 refractive index of that medium 1 is a real quantity. Therefore, N2 divided by N1, that a complex one is divided to that of real one. Overall it is a complex form, and the division just like real part to that of real part and imaginary part to that of imaginary part. N2 by N1 is nothing but refractive index of second medium with respect to first. Refractive index of second medium with respect to first. What is the refractive index of the second medium? That is the refractive index of metal, as we prefer in that particular situation, comparing to that of refractive index of second medium. Second medium is non-conducting dielectric medium. Overall it is a complex one. Its complex one notation as N, that of complex form we write it as 1 plus Ik. K term will be there, that is that imaginary part. Now N overall we represent for that of refractive index. That is why here N is equal to, here N will be how much? As we compare this one to this, so N will be how much? C alpha by omega N1, C alpha by omega N1. As we divide N2 by N1, N1 is real one, so the term will be C alpha by omega to N1 for that of N, and here N I N K. So when we compare to that of imaginary part, it will be N K is equal to C beta by omega into N1, C beta divided by omega N1. Okay. These substitutions are made for what reason? Let me show it, so that looking that expression EOT divided by EOI, EOT divided by EOI at that parallel situation is equal to 2 divided by 1 plus N2 by N1 is equal to 2 divided by 1 plus, what is N2 by N1? Here N2 by N1 is equal to N whole into 1 plus Ik, which is equal to 2 divided by N plus 1 plus I Nk, N plus 1 N Ik. For a perfect conductor, alpha is equal to infinity, that is the attenuation constant, the real part we show here, alpha is equal to infinity. Then that term, as we say, N whole into 1 plus Ik it tends to infinity, as alpha tends to infinity, therefore n whole into 1 plus ik also tends to infinity, that numerator denominator part tends to infinity. That is EOT divided by EOI parallel will be 0 for a perfect conductor. For a perfect conductor, that one is 0, therefore EOT is 0. What is EOT? This is the amplitude of electric field vector for that of transmitted wave. That is, the field inside the conductor is 0. EOT, as we say, when that electromagnetic wave incident normally, then we show that the transmitted wave of that of electric field vector component will be 0, means there will be no field inside that of conductor, no field inside that of conductor. In other words, technically we can say it as the skin depth is 0. The skin depth or penetration depth is 0 in case of perfect conductor. In case of perfect conductor, the skin depth or the penetration depth will be 0. So, all the incident energy is reflected back by the perfect conductor. All the incident energy, that incident on that of metal conductor, now reflected back totally. We show it mathematically. The field inside that of conductor is 0, means the skin depth is 0 in case of perfect conductor, and all the incident energy is reflected back by that of perfect conductor. Next, we showcase what be the reflection coefficient. Since there will be no transmitted wave component, only reflected wave component will be there. So, reflection coefficient can be easily calculated. To calculate that reflection coefficient, also E over EOI parallel term is needed, that is N2 by N1 minus 1 divided by N2 by N1 plus 1. What is N2 by N1? N2 by N1 is N whole into 1 plus IK minus 1 divided by N2 by N1 N whole into 1 plus IK minus 1, sorry, plus 1. Therefore, EOR to that of EOI at parallel situation, that is n minus 1 the real part, I n k imaginary part. Next n plus 1 real part plus I n k imaginary part. Let equation number as A. This one is needed to calculate the reflection coefficient. Therefore, the reflection coefficient is given by the reflection coefficient R at that of parallel situation, means E vector is parallel to that of plane of incident. So, E over divided by E y magnitude square, E over E y magnitude square, that is n minus 1 square plus n square k square divided by n plus 1 square plus n square k square. It is a complex term. Its magnitude as its square, real term square plus imaginary term square under root and its square. So, I write it, its under root and overall square. So, only the terms under that under roots are there, n square k square, n plus 1 whole square. Formula we can write n plus 1 square minus 4 a minus b whole square, a plus b whole square minus 4 ab, 4n plus n square k square divided by n plus 1 whole square plus n square k square, n plus 1 whole square plus n square k square, that is 1 minus 4n divided by n plus 1 square plus n square k square, that is for R parallel. This is equation number, let equation number 11. Then the value of n and k is put here. So, for good conductor n is equal to C alpha divided by omega n1, that is C by omega n1 in place of alpha. For good conductor we already derived for that of alpha is equal to omega mu 2 sigma divided by 2, omega mu 2 sigma divided by 2. This is n is equal to C alpha by omega n1, that is from here n is equal to C alpha divided by omega n1. So, n is equal to C by omega C mu 1 epsilon 1, that is for n1, mu 2 omega sigma divided by 2 under root. So, we obtained n is equal to CC cancelled out that of under root term as sigma divided by 2 omega epsilon 1 under root. Why we prefer like this? As we say omega 1 is equal to omega 2 and n is very greater than 1. Also in this case, means in that of good conductor, K is equal to 1, as we say that Nk is equal to C beta divided by omega n1. Nk C beta divided by omega n1. So value of K is equal to 1. So equation 11 becomes, so equation 11 becomes R parallel is equal to 1 minus 4n divided by n square plus n square. In place of k we substitute 1, in place of nk we substitute that value, and it is simplified in that manner. So R parallel will be 1 minus 2 by n, or R parallel is equal to 1 minus 2 divided by, in place of n, that is sigma under root 2 omega epsilon 1, or R parallel is equal to 1 minus 2 whole into 2 omega epsilon 1 divided by sigma under root. That is the expression for reflection coefficient. When an electromagnetic wave incident normally to that of conducting medium, and that will be the reflection coefficient. So the reflection coefficient increases with decrease in frequency. It is under root of omega for low frequency and high conductivity. For low frequency and high conductivity, the value of reflection coefficient for low frequency and high conductivity, that term is neglected. So R parallel is equal to 1. The value of reflection coefficient R is very near to unity, very near to unity. So here with the help of this video lecture we understand the concept of metallic reflection at a normal incidence situation. Non-conducting dielectric medium, this is conducting medium for medium 1, for medium 2, electromagnetic wave incident normally. The expression for incident, reflected and refracted waves, but for medium 2 K2 is complex one, and that value of alpha and beta are written, and for good conductor situation this factor is very greater than 1, therefore alpha is equal to beta, that value will be this much. At interface we apply the boundary conditions by taking E vector is parallel to that of plane of incidence. Its tangential component at medium 1 is same as the tangential component of medium 2 of that of electric field vector. For normal incidence these angles are 0. Next, the boundary condition for magnetic field vector, relation between electric field vector and magnetic field vector is put it. For non-magnetic medium this value is equal to that mu naught, and the relation in between refractive index and propagation of that of wave vector, adding we have EOT divided by EOY at parallel situation, and EOR to that of EOY at parallel situation. it is further simplified to showcase what be the value of EOT. That factor is used N2 as complex, but N1 is real. So, N2 divided by N1, that is the refractive index second medium with respect to first in terms of N. So, value of N and value of Nk. So, EOT divided by EOY at parallel situation. For good conductor, alpha tends to infinity. So, that factor also tends to infinity. So, this result will be 0. So, EOT is equal to 0 for a perfect conductor. From that expression, it is clear that there will be no field inside a conductor, means the electric field inside the conductor is 0. In other words, we can say the skin depth is 0 in case of a perfect conductor. So, all the incident energy is reflected by the perfect conductor in normal incidence condition. Since there will be no component of that of transmitted wave, only existence of reflected wave component, therefore reflection coefficient is calculated. To calculate a reflection coefficient, first we simplify that one, and putting that value, its magnitude, square of real part and square of imaginary part under root whole square, and the reflection coefficient expression for good conductor situation, that n value and k as 1 and k is equal to that much. So, the values are put here and we obtain the expression for reflection coefficient. From this, it is clear that the reflection coefficient increases with the decrease in that of frequency, means for low frequency and high conductivity, that value of reflection coefficient is very near to unity. So, with this useful and informative notes, let me wind up the session. Thank you.